Trigonometry, the branch of mathematics concerned with angles and how they relate to the side lengths of triangles, gives us satisfying functions like cosine and ridiculous abominations like this expression. Seriously, why is it like this? If you've already seen this problem before, you might know that you can solve it with both geometry and complex numbers, but I'll show you two more really elegant solutions. If you haven't already solved this, I do encourage you to try it. Okay, here are the ways to do it. This first solution is this one you may know, where you draw a 2x1 rectangle made of 2 unit squares. Remember that the tangent is the opposite side over the adjacent side of a right triangle. If you draw this length, then this angle is arctangent 1/2 because the opposite side is 1 and the adjacent is 2. Now rotate the whole segment and its squares by 90 degrees, making this perpendicular segment. This length is also arctangent 1/2 because of alternate interior angles. You can now draw this length, making this angle arctangent 1/3 because the ratio is 1 to 3. Now we have a right triangle and an isosceles one too, which makes each of the base angles 45 degrees. Now we know that arctangent 1/2 plus arctangent 1/3 is 45 degrees. Arctangent 1 is clearly 45 degrees, as you can see here, so arctangent 1 plus arctangent 1/2 plus arctangent 1/3 is 90 degrees total. The second solution that you may have seen uses complex numbers. Typically, you might think of complex numbers as rectangular in the form a plus bi, but just as Cartesian coordinates have polar coordinates, complex numbers have a trigonometric form, which is r times cosine of theta plus I sine theta, where theta is called the argument and r is the magnitude. When you multiply complex numbers, you add their respective arguments and multiply their magnitudes, which I guess you can see from their exponential form. Anyway, this means that when you add angles, you can just find the angle of the product of the complex numbers with those arguments. Since tangent is the ratio of sine to cosine, it is the ratio of the imaginary part to the real part, ignoring the I. For arctangent 1, we find the complex number with imaginary part to real part equal to 1, which can just be 1 plus I. For arctangent 1/2, we use 2 plus I, and arctangent 1/3 use 3 plus I. Multiplying these three numbers gives us 10I, which lies here on the complex plane. Thus, the angle is 90 degrees, or pi over 2 radians. The third solution brings us into uncharted territory. Since we're on the topic of a trigonometric solution, let's try to use trig identities. Specifically, tangent of a sum of angles looks pretty useful now. Tangent of arctangent of alpha equals alpha, and tangent of arctangent of alpha plus arctangent of beta equals alpha plus beta over 1 minus alpha beta. Thus, arctangent of alpha plus arctangent of beta equals arctangent of alpha plus beta over 1 minus alpha beta. So arctangent of 1 plus arctangent of 1/2 equals arctangent of 3. Then arctangent of 3 plus arctangent of 1/3 equals arctangent of, oh wait, this requires dividing by 0, so you can't take the arctangent of this. No, you can. There's a workaround. Remember complex numbers? Number I has an argument of pi over 2, and the tangent of its angle is 1 over 0, which you can tell from its components. Then, arctangent of 1 over 0 is pi over 2, at least how it converges in this case. You could also take the limit of arctangent of x as x approaches infinity, but no matter how you see it, we already simplified the expression to pi over 2. The final solution I found uses geometry again, and it's the most visually convincing. Draw this 3x2 grid of squares. Construct this segment, which makes this angle arctangent 1/3. It is length root 10 from the Pythagorean theorem. Now construct this other segment, which makes these two lengths root 2 and 2 root 2. Now this triangle is a right triangle because its sides follow the Pythagorean theorem, which makes this angle arctangent 1/2 since we have a right angle. Now this angle is arctangent 1 from this side length. This gives a nice visual proof that the three angles come together to form a right angle. Don't you think it's so elegant how that horrific atrocity at the beginning fits so nicely to make this? And isn't it nice how there are so many approaches to solve it? And isn't having lots of rhetorical questions to end this amazing? That's all there is today, but there will certainly be more puzzles like this. Bye.